You can build a mathematical model around your grinding and flotation plant using MetSMART. In order to build the model, you need survey data and you need to have mass balanced the data. Now, what does it mean to build a model? So, every equipment piece is represented by a set of equations, and these equations have an input and an output. This input and output has been calculated with the mass balancing step. There's also structural dimensions, which we have entered in step number 2. Operating variables, which we have entered during the survey data. Also equipment outputs, which we have entered as part of the survey data. So the only missing component is the calibration constants here. The calibration constants is effectively the mathematical model of the plant. After the mass balance is performed, we have smoothed data which we can use to build a mathematical model around each equipment piece. So when I do this calibration, I will use the survey information that was entered for each equipment piece, and I will use the mass balanced result of step number 4. So to calibrate each equipment piece model, I simply have to click on the Calibrate Models button. Within a few seconds, I receive a message which tells me that my calibration is complete. So to view the results of each calibration, I have to click on each equipment piece in the flowsheet. So firstly, we will look at the size distribution graph. The blue dots represent the survey. The orange line represents the mass balanced result, and the red line represents the calibration result. From this graph, you can see that the model fit is very accurate. So this is a very good model fit that we achieved. At the bottom, you can see your calibration constant results. So what this means is that this information here, these numbers, they represent the mathematical model of the sag mill. So for example, for the breakage rates, you will see that as your particles become bigger, the breakage rate goes up to a maximum, and then at around 60 to 70 millimeters, you have a very low breakage rate. This is the critical size of the charge, and then you have quite a sharp increase in the breakage rate, and this shows that there is a lot of abrasion happening inside the charge. So for the power draw calculation, this is our calibration result. For the slurry filling, this is the number. And then, very importantly, with MetSMART, we can predict the hardness of the ore in the sag mill during operation. So you don't need to do various tests on the ore sample that is going through the sag mill at that time. Now this deserves a discussion on its own, and for this we have a document which explains exactly how this number is derived and how it works. In short explanation, this hardness index is from 0 to 100. 0 is the softest and 100 is the hardest. So during this time, the ore was had an index of 62, which indicated that it was probably a medium to hard or hardness during that operation. The next equipment piece that we can look at is the cyclone. Now for the cyclone, you can see here that we had quite a good fit again on the underflow and the overflow. So the dots represent the survey, and then the colored lines represent the mass balance and the calibrated result. Now, every time we have a calibration constant result, it is accompanied with a full explanation of what the results actually mean. So here, for example, you can see the D50C is the cut size of our cyclone. Now the constant used to calculate this number is given here, and then the actual D50C number is also given. The same with the water split, we have our constant and then the actual water split. Same with our pressure and then the sharpness of the separation. If we want to see our efficiency curve on the cyclone, we can click on the efficiency curve, and here you can see the fraction of your feed reporting to the overflow for each size. Then we can look at the ball mill. Again, this is quite a good model fit that we've achieved here, with the calibrated distribution very close to the mass balanced distribution. Again, if we have a result, we need a full explanation of that result. So for example, here we have our breakage rates for our ball mill. If we want to look at the graph, you can see that our breakage rates increase up until a certain point where the slope starts to go down. Okay. If the breakage rate has gone down dramatically over here, it would have indicated that there was possible scats forming inside the ball mill. Same thing for the trommel. In the trommel we can again see the efficiency curve of the trommel, and here you can see the fraction of the feed reporting to the undersize. So now we have a calibrated mathematical model around the circuit. Now this is an exercise that you can do yourself on your plant, or you can get consultants like Minerality to perform a plant survey, a mass balance, and then build a mathematical model of the plant. When you have a mathematical model of the plant, you can start doing simulations around the circuit.